Hello again. Now, we do a thing at my school called Period 6. Now, what this is an extra period after school where the Year 11s come in and they get more help, which is brilliant. I love doing it. I get to stay at school even longer. It makes my life joyful. Anyway, I've been asked by one of my students to can I go through the stuff and make a video of what I'm saying as well as actually doing it so she can rewatch it and whatnot. So here we go. I am now going to talk about the stuff I spoke about in my last one, and I'm going to make a video about this stuff. Just get my pen on. So where's my mouse? So I started off by speaking about variables. Okay, I'm just going to write on here variables. Okay, now we obviously know that our independent variable is the one we change. Our dependent is the one we measure, and our control we keep the same. Now, they might ask you various things rotating around these. They might ask you, they might ask you to identify these variables. They might ask you to explain how you control it. So if your control variable is a volume of acid, they might say, how do you control this? And you would very simply say, look, I make sure I use a measuring cylinder or a pipette to measure that volume, so on and so forth, just to make sure you're all happy with that. There's nothing massively complicated about that, but it's important to think about it nonetheless. Now, we then moved on to think about some elements. So we've got group 1. Now, group 1 are in group 1 of the periodic table. Okay, they have 1 electron in the outer shell. This makes them group 1, obviously. Now, we know this, if we take lithium, okay, with its atomic number 3. All right, we've got we'll do 4 Li, and we'll do a circle. I should do a proper circle, but I won't. I'll draw one. And we've got 2 electrons in the first shell, maximum of 2, followed by the squarest circle you ever did see to give me 1 in the next shell. Now we'll do the next one. Okay, sodium. Now sodium, as we may know, has 11. You don't need to remember this is all on the periodic table. Okay. So we'll then get our first shell with a maximum of 2. Our second shell, that's a bit more circly. Now we're going to put 8 in there. Now that gives us 10 in total. Okay, and then we've got our third shell with 1. So there we go. We can now see lithium with its electron configuration of 2.1 and sodium with 2.8.1. Okay, now why, therefore, is sodium more reactive? That's a good question, and it's a question you're likely to be asked. Why is sodium more reactive? Well, okay, remember, we are trying to, in group 1, we're trying to lose 1, do you know what, I'm going to write it, 1 electron. What I'd like you not to do, don't write an. I know an means 1, you know an typically means 1, but write 1. They like to see the word, okay? Lose 1 electron. Now, in sodium, the outer shell electron, right, is further from the nucleus, from the attractive, try spelling, further from the attractive pull of the nucleus. It is, therefore, easier to remove. Fantastic. Now, you do the exact opposite of that. You can say in lithium, it's closer to the attractive pull of the nucleus, therefore it's harder to remove. That is absolutely fine. Okay, so that is group 1. Now, we're also going to talk here, let's talk very briefly about group 7. Now, it's a very similar story we're going to talk about here. Okay, group 7. Now, save my drawing. Okay, we'll just list these. So these are 2.7, okay, and then we've got chlorine, which is 2.8.7. Now, here, remember, they're trying to add 1 electron. How are you going to fill the shell? You're going to add 1 electron, okay, so fluoride will have 2.8 and so on and so forth. Now, if you're trying to add an electron, okay, in fluorine, the outer shell is closer to the attractive pull of the nucleus. Therefore, it's easier to add 1. Okay, that's just what you need to say. You need to say, in this case, it's the exact opposite, and therefore the trend is the opposite. In this one, they get more reactive as you go up. Okay, and clearly in this one, as you go down, so this way would be down the periodic table, they also get more reactive. So, hang on, I'm doing something here, active, I don't know what the buttons on this pen do, they clearly do that. Anyway, there you go. So, those are group 1 and group 7. So, as you go up, they get more reactive. Now, you need to be aware for group 7 as well about displacement, because if you react chlorine, okay, chlorine with sodium bromide, it will displace it, okay, and because chlorine's more reactive. A more reactive halogen will displace a less reactive halogen from its compound, therefore making sodium chloride and bromine. Now we've got to balance this, obviously you just need 2 of each of those. Okay, I was also asked to talk about redox here. Okay, because that's a chlorine, and here you have a bromide ion. Here you have a chloride ion and bromine. Okay, so that's gone from element to ion. That means it's gained an electron. That's gained. That's gone from ion to element, therefore it has lost an electron. Now, we remember, of course, oil rig, oxidation is loss. So the bromide there has lost an electron, it's been oxidized. The chlorine has gained an electron to become chloride, it's been reduced. Now this is redox, reduction, and oxidation happening at the same time. Redox, lovely. Okay, now let's think a little bit about rates of reaction. Now we know that we're going to have to talk about rates of reaction in terms of particles. Okay, now we're going to use the example I used in the lesson. I used decreasing concentration. So just for fun, I'm just going to do the effect of increasing concentration. So how on earth does that work? So how do you do this question on this? Now the first thing you need to do, right, is you need to talk about the particles. What is the effect of increasing the concentration on the particles? Well, if you increase the concentration, you will have, very simply, more particles. Okay, higher concentration, more particles. Simple as that. Don't talk about energy, that's a temperature thing. You just have more of them. Now, collisions. It's collision theory. You've got to talk about the collisions. Now, remember, you cannot just talk about collisions. You can't say this one has more collisions, therefore it's faster, okay? You have to talk about frequency. So, in this case, if you have more particles, you will have more frequent collisions, okay? I.e., there's a time thing going on there. You're talking about collisions per second rather than just collisions. You know, 10 collisions in a second is clearly faster, you know, than 100 collisions in an hour. You've got to say about the frequency, collisions per second. I like that. More frequent collisions, easy peasy. Now, you then finish up by talking about rate. Okay, so if there's more particles, there'll be more frequent collisions, and the rate of reaction will increase. Okay. Now, the other cheeky thing they'll sometimes throw at you, just to really go whoosh, okay, is they'll say, as the reaction goes on, what happens to rate of reaction, okay? So, if you're thinking about it, when your reaction is occurring, let's make this easy, A turns into B, okay, that's your reaction. A is going to turn into B. Now, you start off, obviously, with 100% of A and no B, okay? So then there are a lot of A particles kicking around, but as A particles turn into B particles, you actually have less A particles kicking around. They've turned into B. Therefore, in this case, okay, the concentration of A particles over time will decrease. This means less particles, obviously. This means less frequent collisions. That means over time, as this reacts, your rate will slow down until it stops. Now you're going to end up with a graph that, oh, that was a remarkably good axis. You're going to end up with a graph that looks a little bit better than that. But yeah, this bit should be horizontal. You'll end up with a graph that looks like that, because you can see that it's slowing down. Okay, that's all you've got to do. You'll get a much better graph than that on your on your exam paper. Nice. Next, we talked about bonding, because you've got to be able to talk about bonding. Okay, now they might ask, for example, you've got a metal, okay, with a melting point, of 1700 degrees C, and then you've got a simple covalent with a melting point of, I don't know, 41 degrees C, why not? Okay, and they're going to say, okay, what's the difference between those? Can you talk about the difference between those two in terms of their bonding? Now, you just need to talk about each one and basically say why that one's higher. Okay, so a metal, as we know, has strong forces. You've got to be able to name these intermolecular forces. What are they? They are electrostatic forces of attraction. You need to know that. It basically means opposite charges attract, right? They are strong. So, as you know, it takes a lot of energy to break strong forces. Okay, so there's a lot of energy to break the strong forces. So it's got a high melting point. Now, in terms of simple covalent, on the other hand, it's got weak intermolecular forces. Okay, they're weak. Now, you don't even know the name of the intermolecular forces in simple covalent for GCSE, and you don't need to know it because there's lots of different ones. You don't need to worry about that. Just call it intermolecular forces. Now, you could also, if they're asking you to compare, of course, you need to say they are weaker than in the metal. Look at what it's asking you to do, okay? If it's asking you to compare them, you've got to say simple covalent is weaker or metallic is stronger. Comparison. You can't just repeat this again. So, weaker than metal. Less energy. This is again a comparison. Required to break weaker forces. Okay, so less energy required to break weaker forces in simple covalent. So now we're going to talk about the melting point. We're going to say lower melting point. Okay, this has all been about the comparison here, hasn't it? We've talked about how they are weaker, less energy required to break them, so a lower melting point. You are comparing, those are comparing words. I could have just gone ahead with the same description again for the metal, weak forces, not much energy required to break them, low melting point, but if it asks you to compare, you need to do some comparative words like weaker, lower, you know, comparing. Nice. Now, the next one was bond enthalpy. Now, we spoke about bond enthalpy. Now, they always give you a bond enthalpy question, okay? Now, this may be called bond energy, whatever it is. Now, we know, for example, this is, okay, your HH bond, okay? Now, when you break this, you have to put energy in. So it's endothermic. It is, okay? When these are formed, it's energy out, and this is exothermic. Now, all you do with these, very simply, okay, is you work out your energy in based on whatever they've given you to whatever reactants are present. How much energy is required to break all the bonds in the reactants. You then work out your energy out. Energy out. Essentially, how much energy is going to come out when all the bonds are formed in the products. You then do in minus out to work out your overall bond energy, and then you just write it down, whatever it is. Now remember the sign for this fourth point, this is number 4, it's just your answer. You've got to get a sign correct, okay? So if it's -3, write -3. If it's 3, write +3. Make sure you write a plus. Always write a plus so it shows it's positive. No ambiguity, you're saying it's +3. Now, realistically, you don't always do this, but for this one, where the answer could be negative or could be positive, just be clear. So your examiner knows you know what you're talking about, okay? You've got to get a sign correct for that fourth one, okay? And if they ask you, your bond enthalpies here will be in kilojoules per mole, okay? Kilojoules per mole. So you've got to make sure you give your units down here if not provided. Nice. Now the next thing we talked about was the properties of fractions. Now this is, for example, saying if I've got some petrol, okay, you've got to learn the fractions of your fractional distillation. This uses fuel in cars, okay. Now again, they might ask you why, okay. It's very flammable. It's very flammable, for example, that makes it good. It's a liquid, which makes it easy to move around. Just got to talk about that. Now remember, as we go down and we got more carbons in chain, what happens to our various properties here? Well, first of all, flammable. Okay, as you go down and you've got more carbons in chain, it gets, what do you think? Less flammable. Good. As you go down, it gets less flammable. Methane at the top is the most flammable. As you go down, they get less flammable. Now, we've also got melting / boiling point. Okay. Now, the one at the top, methane, is a gas. The one at the bottom, bitumen, is a slurry liquid. So therefore, these increase. As you go down, they get higher. Now, the last one is viscosity. Viscosity. Now, I always like to relate this to runniness. Okay, how runny is it? I like the word runny, but it's the opposite of runny. Okay, what does that mean? If something's runny, it flows very well. Okay, but that means it's not viscous. If something's not very runny, it doesn't flow very well. That means it's really viscous. Okay, so very runny, not very viscous. Not very runny, very viscous. Now what does this mean? As you go down, they start off as a gas which flows very easily. Okay, they are very runny, which means they are not viscous. That means as you go down, the viscosity increases. Brilliant. What else is on my little thing here? Right, dot and cross diagrams of various things in the atmosphere, such as carbon dioxide. Now you know carbon is in group 4, which means it has 4 electrons in the outer shell. Oxygen's in group 6, which means it has 6 electrons in the outer shell. So what we're going to do is, we've got carbon here with its 4. We're going to draw them like that for reasons which will become apparent later. You've then got oxygen, which has 6. Now, carbon needs, from this oxygen, it needs to get 2 more on this side, which means it's going to have to put both of its 2 in. Okay, therefore oxygen will put in 2 of its electrons as well, of 6, meaning there'll be 4 electrons left kicking around. Now, it doesn't matter where you put the pairs, one up there, one down here, or whatever. I'll draw the same on the other side. We've got 2 there, and again, if you want to do a pair up there and a pair down there, it doesn't matter where the pairs are. It doesn't have to be pairs, you can just draw them around it if you like. You can dot them any old way around it doesn't matter. I draw them in pairs, looks easier, and it's easier to count. Again, make the examiner's life easier when he's marking your stuff. Okay, now we're going to have to talk about percentage by mass. Okay, so essentially how much, what's the percentage by mass of oxygen in H2O? Okay, now oxygen has an atomic mass of 16 and H has an atomic mass of 1. Therefore, if you're thinking about it, you've got 2 H's, which is 2, and you've got oxygen, which is 16. 16 of that 18 is actually oxygen, okay? Because it's got a total of 18. 16 of that is oxygen. Most of it's oxygen by mass, okay? So once you work that out, times by 100. to get your percentage. Now you may be asked to do that. You may be given an option. Let's just say my first option, A, what is the percentage by mass of oxygen H2O? Let's go with 3%. Okay, and for B, now I remember in the period 6, I actually, off the top of my head, pulled the correct number here. I don't know how I did that. It was a complete and utter random guess. I think the number I used is 88%, so we'll go with that. B is 88%. Now, you might say, which one of those two is the percentage by mass of oxygen? Well, I mean, you could work it out. You can, but actually, if you think about it and you understand what percentage by mass means, and you understand what the molecular masses of oxygen and hydrogen are, it's got to be the 88%, hasn't it? Because it's the only one that's going to be remotely close. It's most of it is oxygen, therefore it has to be that. Nice. Now, alkenes. Let's go back there. Let's do some hydrocarbons. So we've got alkenes. Now, they will decolorize bromine water. They will decolorize bromine water. Okay, so basically, if you start off with this bad boy, it doesn't matter what alkene it is, it'll do exactly the same thing. Okay, and you add Br2 to it. What will happen is, essentially, you'll end up with this. The bromines will break the double bond and just join on either end. Doesn't matter what the alkene is. Again, like your polymerization, I would draw the alkene like this, front and center, and then branch everything else off it, and there you go. That is what happens. Okay, so in this case, we've got C2H4 plus Br2 will actually give us C2H4 Br2. Okay, that's the equation. Okay, that was pretty much everything I spoke about in period 6. I had a little waffle about that kind of stuff. Brilliant, fantastic, thank you for watching, and I will see you all soon.